Hello everyone. So in the previous part of the lecture we had discussed uh, the question what is going to happen if we consider the finite strain tensor as we had seen here, but we considered that these linear terms have very small magnitude. So this is the first important note we are going to consider. So if this generic term del ui del xj, it has a very small magnitude, meaning that this is very much less than 1. And you please note that let me write that properly. This is much less than 1. So you please note that this entire term, the del ui del xj, that is dimensionless, meaning that ui, that is a component of the displacement vector, and it has the dimension of length. Similarly, the xj, it is a component of the position vector, and it also has the dimension of length. So in the numerator and denominator we both have length, so overall this term has is dimensionless. So it is perfectly alright to say that the magnitude of this term is much less than 1. We don't need to put any unit here. But what is the implication of this? That if this is true, the magnitude of this term is much less than 1, then you can see, if we go back to the previous page here, that this magnitude is much less than 1. Let's say it is something like 0.1 or perhaps even less than that, and this also has a magnitude which is much less than 1, because you note that when you are writing this is a generic term. It does not mean that we cannot be considering this equality to be not holding true if we perhaps write this as del uk del xj. This is a generic term. It does not mean that here, if we come back, it is only this del ui del xj which can be less than 1. This is a generic expression. You might as well have written this as del up del xq or del um del uxl. Anything goes. So this generic term, if it is much less than 1, then this one and this one, the multiplication of them, suppose this is 0.1 and this also is let's say 0.2, then this becomes overall 0.02, which is even less than 1, even smaller. So you see, this is like 0.1, this is like 0.1 of that order, and this is one order less than that, because it's a multiplication of two small numbers, both less than 1. So we may, to a good engineering approximation, say that if this is holding true, that the del ui del xj magnitude is smaller than 1, then for all intents and purposes this quadratic term can very well be dropped. Okay, so under this consideration we can say that Eij is approximately equal to half of del ui del xj plus del uj del xi. We do not write anymore under this consideration the quadratic terms. Now this particular expression, it no longer contains any quadratic terms, and this particular form is defined to be this thing, epsilon ij. So we say, or we define, that whenever we have this particular combination, we define that to be equal to epsilon ij. So earlier we had written it in the reverse fashion, that we had written a symbol like this, that colon equal to, that is the so if you have a symbol here, so whatever you write on the right hand side, that will be the definition for this, And here what we are doing is we have an expression and then we are choosing to define that expression in this form. So it is just the reverse way. So with this understanding, you note that this has a very special name. So earlier we had seen that the Eij, capital Eij, that is referred to as the finite strain tensor. Now with this new definition, the epsilon ij equivalent to this is the infinitesimal strain tensor. Sometimes it is also referred to as small strain tensor. Okay, now just as we had discussed earlier, this epsilon ij having in its subscript two free indices, that is also a second order tensor. So again, just like Eij, so let me just quickly refer back to the previous slide. We had said that this is a second order tensor, so is epsilon ij. Eij is equal to Eji. Similarly here, epsilon ij will be equal to epsilon ji. So symmetric. And you see that this Eij can be represented as a 3 into 3 matrix. Similarly, this epsilon ij can also be represented as a 3 into 3 matrix. However, we are not going to write down just for the sake of repetition this epsilon 1 1, epsilon 1 2, all these things. Instead, what we are going to do is something which is very much practical and useful for the purpose of our current course of mechanics of solids. So in many textbooks you will see that this kind of an index notation is hardly ever used, primarily because those textbooks are aimed at first year engineering students, but you are no longer first year engineering students, rather you are third year engineering students. What is so the connection between that kind of a notation and this index notation, where you are using x1, x2, x3, is that so we can say that the x1, it corresponds to small x, the x2, it corresponds to y, and the x3, it corresponds to z. So what I'm trying to do here is to establish a connection between this very general mathematical framework and the more common mathematical framework which most of you are familiar with, which is referred to the rectangular Cartesian coordinate system, where the coordinate variables are the familiar x, y and z coordinate system. So if we fall back to that kind of framework, what happens is that correspondingly the different components of the displacement vector that are given by these. So u1 corresponds to u. So this is simply a change of notation, so to speak. The u2 is given by v and the u3 is given by w. So overall what we can say is epsilon 1 1, that is epsilon xx in this new framework, and that the expression of that is del u del x. We don't even have to use a bracket, so we can remove this thing. We also don't need the half, because you see what we are basically having here is half del u1 del x1 plus del u1 del x1, so that is just del u1 del x1, and that is nothing but del u del x. So this is simply del u del x. For epsilon 2 2, what we have is that is epsilon yy, and that is nothing but del v del y, which corresponds to del u2 del x2. Epsilon 3 3, that corresponds to epsilon zz, and that is equal to del w del z. Furthermore, we have for epsilon 1 2, that is epsilon xy, and you understand that epsilon 1 2 is equal to epsilon 2 1, so epsilon xy is equal to epsilon yx, and that is equal to, now here we need the half because they don't add up like before when we had the expression for epsilon xx. So you understand here that this del u del y, it is coming from del u1 del x2, and this del v del x, it is coming from del u2 del x1. Similarly, epsilon 2 3 is going to correspond to epsilon yz, and that is equal to half of del v del z plus del w del y. And finally, epsilon 3 1, that corresponds to epsilon zx, and that is equal to half of del w del x plus del u del z. So just for the sake of completeness, I will write this as very explicitly as this is equal to epsilon yx, and this is equal to epsilon zy, and this is equal to epsilon xz. Now these first three terms, epsilon xx, epsilon yy, epsilon zz, these are referred to as the normal strains. Or the normal strain components. Whereas these three, rather these six, because actually you have epsilon xy is equal to epsilon yx, all these six, they are referred to as the shear strain. Now every year I teach this, there is always a little bit of a confusion corresponding to what you perhaps had learned in your first year, because I think some of you came across the term gamma xy or gamma yz in your first year mechanics books, and perhaps that was referred to as the shear strain. So there is no confusion actually. You can just note down that whatever we have defined like this here, the epsilon xy, that is nothing but half of gamma xy is equal to half of gamma yx. Similarly, this thing, whatever this expression we have found out, that is equal to half of gamma zy equal to half of gamma yz. Similarly, this thing is equal to half of gamma xz is equal to half of gamma zx. So it is just from the context you can understand like which expression you have to use. So if gamma is used, don't use the half here and just write down these expressions, and if epsilon is used, so just use the half here. Okay, uh, so overall what we can say is that these relations that we have written down here, primarily the six independent relations, or epsilon xx, epsilon yy, epsilon zz, and epsilon xy, epsilon yz, and epsilon zx, these are referred to together as the strain displacement relations. So uh, the expressions of epsilon xx, epsilon yy, sorry, epsilon zz, epsilon xy, epsilon yz, and epsilon zx in terms, sorry, in terms of the derivatives in terms of the derivatives of the displacement vector components, that is del u, del x, del v, del y, all these things that we had obtained earlier. uh, so all these expressions, they are referred to as So I'm writing this in capital letters to denote how important these relations are. These are referred to as the strain displacement relations. You note down very quickly that we are no longer referring to this as the small strain or the infinitesimal strain. So in the absence of any special qualifier, whenever you come across the word strain, you understand that implicitly it means the infinitesimal of the small strain tensor. So the strain displacement relations are what we had obtained in this part here. Okay, and these will be extremely important, these strain displacement relations, uh, as long as you are talking anything related to mechanics of solids or elasticity in general. It will be extremely important for solving various problems as well as for developing our theory. Okay, now very quickly we'll just write this strain tensor in the matrix representation. So because this is such an important topic, I am spending a lot of time in representing the things in various forms. So this is a W, this is W. So this term that I have just written here is exactly the same as this term. Again, this term that I have just written is exactly equal to this term. And this term that I have written is exactly equal to this term. And finally, we have this. So this is in the form of a matrix. So all these strain displacement relations, they are encapsulated in this kind of a matrix form here. Okay. So one final thing, the earlier expression that we had obtained, so this one, this thing, so under the consideration that del ui del xj, this magnitude is much less than 1, what we have is this thing is equal to epsilon ij, because when we have already seen that when this is true, so eij is approximately equal to epsilon ij. So this is what is holding true now. All right, so in the next part of the lecture we are going to discuss how we may further re-represent this particular equation in a slightly more convenient form. Okay, thank you.